This podcast is brought to you by LMU Munich.
So, thank you very much. In fact, I'm very glad to be here in Munich. It was because Munich was my first job. First time I worked in my life was in Munich. Very few, practically none, was born at that time when I was here working in Munich. So very glad to come back. So today I will talk about something which is, I think it's very interesting, but, and I'm sure that at least Slava will agree with me that it's very interesting, but we have to confess and admit that we are in the minority among theoretical physicists that think that this subject is very interesting. Nevertheless, well, I will talk about it and I will say why I believe it's interesting. So, the thing is gauge theories and the non-commutative geometry, and I was asked to give a review of it. So, well, the first motivation to introduce non-commutative geometry in space, not surprisingly, came from Heisenberg. And, well, the thing that we will not follow everything there, but Heisenberg wrote, he never wrote anything. He did not write any paper on it. But he wrote a letter to Peierls, whom we shall see in a moment what he did with it, who talked to Pauli, who talked to Oppenheimer. At that time, Oppenheimer had, that was in the late 30s, and Oppenheimer had a student, a graduate student, who was Mr. Schneider. And he gave Mr. Schneider as a thesis topic to solve this problem. I mean, not very precisely given, and he left. Because, as you know, Oppenheimer was doing, during the war, other things, was not interested in non-commutative geometry. So Mr. Schneider was left alone, and nevertheless, he managed to do something. In 1946, he finished. And, well, the motivation was very simple. You know, in the quantum mechanical commutation relations, x with p is h bar, solve, if you take the hydrogen atom, solve the 1 over r singularity. Classically, you have a singular potential, so there's unstable. The classical atom is unstable, and quantum mechanically it becomes stable. And I say solve in quotation marks because it solved the 1 over r. If the potential were 1 over r squared, they wouldn't solve it. I mean, quantum mechanics does not solve all singular potentials, just the 1 over r potential. So that was the idea. So since quantum field theory had short distance singularities, let us introduce further non-commutative structure, not just in phase space, but also in real space, in ordinary space, to solve short-distance singularities. Nothing really came out. Schneider wrote a paper in which he does not address the problem of the singularities. He did not know how to do that, although in the introduction he repeats the motivation. But he tries to find a set of commutation rules which he wants them to be compatible, in quote-unquote, with Lorentz, be Lorentz covariant in some sense. So he writes some kind of commutation relations, for example, well, the xy and z are the space coordinates. So he has a parameter, A, which is this deformation parameter, which is on top of h bar, right? So it deforms, he deforms Heisenberg's algebra with another parameter, deformation, which is called a square. So in the limit a square, you get back the Heisenberg commutation relation in which x and y equal 0, commute, right? But then he puts, and this is the commutation relation, say, with x and px, which is 1, which is the usual one here, plus this deformation parameter, right? And then he put some strange commutation relations between t and x, with this is the generator of Lorentz transformations, and the same x and p, well, etc. Anyway, so he has this paper. What is important is that there is no mention of Oppenheimer in the paper. He does not thank his supervisor. Apparently, he was not very happy with being left alone all this time. And what is interesting is that this Mr. Schneider was a very clever man and became very famous later, but he changed completely the field. Instead of working in theoretical physics, he became accelerator engineer. And he signed the famous paper of the strong focusing, the alternating gradients synchronous method of focusing the beams. And he was one of the three signatures, was Courant, Livingston, and Schneider. So complete change of direction. Anyway, so this is the so much for this question of short distance singularities. Later on, there have been many formulations of, but we shall come back in a moment, but not using this particular scheme. So as far as I say, this scheme is not very consistent, so it's not surprising that it's not used by anybody else. But the idea of formulating, say, field theory in a space with non-commutative geometry has gone quite, there have been several studies. So let me go to the second motivation, which are external fluxes. Independently of what happened, Landau in 1930 solved the problem of the electron in an external magnetic field, right? And the thing that you find in standard quantum mechanics undergraduate textbooks, right? The Landau levels. So the important thing, of course, is if you have a magnetic field like that and you have an electron moving, the important motion is the projection in the perpendicular plane, the xy plane. And classically, it's a center. It's a circle, right? You can compute the center, the coordinates of the center. Quantum mechanically, what Landau showed is that you get a quantized the Landau levels. Sorry, and that the two components of the velocity, x and y, do not commute anymore, and they get this B, the magnetic field. And the same way, if you want to compute the coordinate, you can compute the coordinates of the center of the circle, right, the classical center of the circle, and you find that the two coordinates, x and y, do not commute anymore. So you cannot measure the center exactly simultaneously, x and y. So this was the classical Landau result. And now comes Peierls in 1933. He was the one who received Heisenberg's letter, and then went the other way around. He said, well, let me study the motion. He found out what is the commutation relation between x and y that would reproduce that, which is this thing here, 1 over b now. So he solved the problem of a free electron in a space with non-commutative geometry this way. In fact, was at the limit of large b, so he obtained the lowest Landau level.
And what is b here?
Pardon?
What is b?
B is the magnetic field. The
Free
external
electron,
magnetic
but
field.
moving
Yeah,
in
you have a
magnetic
magnetic field and you have. So this is just for Peierls. This is only the deformation parameter, right?
Yes.
But for Landau, it is the magnetic field. So this is the.
So b is non-commutativity.
Yeah, exactly. It is the deformation parameter, and you find out. So this is the, as far as I know, the first concrete physical result that has been obtained using ideas of non-commutative geometry. And as we know today, in most model string theory or whatever you want to do, you find external fluxes are very often part of the problem, of the solution. So in that respect, this is something that has come to stay. Right? This is formulation that is very useful. Other motivations later on, much more recent motivations. So one of them was the Seiberg-Witten map, in which they showed that in some sense it is an equivalence. It's not something that you have to assume as extra. If you write a gauge theory, you can always reformulate it, and I will give an example in a moment, as a theory in a space with non-commutative geometry. So in some sense, non-commutativity is part of the non-commutativity of space, or at least part of the space, is really included in the concepts of gauge theories. And this is to my taste at least, it is the result, the most important observation, that somehow it's not another assumption, extra assumption. The fact that you are doing non-abelian gauge theories, somehow the non-commutativity of non-commutative geometry is built in. And that's what we... So this was one. Then the one that I will talk a little bit more is large N gauge theories and matrix models. It was known already many, many years ago that at the limit of when you take SUN at the large N, you can reformulate the theory as a matrix model, and then you have non-commutativity. And then I will talk about some more recent thing, the construction of gauge theories using the techniques of non-commutative geometry, in which case the emphasis will go the other way around. You start with the mathematics of non-commutative geometry and you try to see what kind of theories you get, and you get gauge theories, which is an important thing. And finally, I will talk a little bit about gauge theories and quantum gravity. So this will be the thing, more or less. So now, today, we don't follow the thing that Snyder did, namely to have commutators with the Lorentz generators on the right-hand side. But there are several ways to introduce non-commutativity. This is the simplest case in which you have theta x mu and theta and x nu here, some theta mu nu, and let's say theta constant, which I will call the Heisenberg case. You see, when Heisenberg deformed the algebra of ordinary numbers, functions, right, introduced a parameter h bar, which deforms the algebra, right? But the deformation was the simplest possible. The commutator was proportional to the unit matrix, not to another operator there, right? So that means that if you go to second to turn around, you end up very soon. It's not. This is the Heisenberg case, which I will. Then you can make it more complicated if you want. This is what I will call the Lie algebra case, in which x nu has again an x here, right, with some matrix here, right? Or the quantum space case, etc. So there are several ways to introduce non-commutative geometry, and we shall see some in a moment. In all these cases, you have eventually to define a derivative operator, right, which is this thing here, and to define what I will call the star product, which is the product of two functions. You know how to define f times g, right, when they depend on x, which don't commute among themselves. And this is a standard way of doing, and it has, again, a very old history, which I will not go into in detail. And this star product contains this theta parameter I have here, and in most cases, when people want really to make calculations, they do an expansion in powers of theta, which is maybe not the smartest thing to do, but nobody knows how to do the real smart thing. So good work for young people. So that's what I want to say. It's not the most efficient way, and we shall find out in a moment. We shall see that for quantum field theory, if we want to do gauge theories, this will be a problem. Now, for the next quarter of an hour or 20 minutes, I will go to this motivation I said before with large N field theories, right? Which again would show that they come, non-commutative geometry comes naturally. So, simplest way. Suppose that we start with a scalar field with an index I, goes to I goes from 1 to n, it's a vector model, and goes to infinity. Then phi I, you can always write it as phi of sigma of x, put an extra coordinate sigma. Sigma goes from 0 to 2 pi, it's a circle, right? And what you call here phi I is just the Fourier component of that, and so the mass term will be phi I will be integral d sigma phi square, right? So you say, well, with the price of going to 5 dimensions, you have local field. However, the trouble if you do it this way is that if you try to do the phi to the 4th term, then you get the square of the integral, so it's not local in sigma anymore. And the real observation that made, which is almost trivial to think of it, is that if it's not a vector model, but the field belongs to the adjoint of a SUN group, then this 4th order term is local. So for SUN, for gauge theories, the corresponding term is local. This is the important observation. And for a Young-Mills theory, the resulting expression is local. So let me just show you how it goes. Take an SUN Young-Mills theory in d-dimensional space. So you can write the vector potential this way, with these are the matrices in the adjoint representation. The claim, which I will prove, is that there exists a reformulation in d plus 2 dimensions, right, of the theory, where a mu becomes x. You introduce two new dimensions, z1 and z2, f mu same z1 and z2, and the z1s and z2s satisfy this commutation relation. So they are a surface, but really a fuzzy surface for n finite. When n goes to infinity, they become a real surface, commuting coordinates, right? So this is the thing, and then the commutators become the Moyal brackets, and the same thing, that's the gauge transformation, is the Moyal brackets, and f mu nu becomes the star product.
So Z1 and Z2 are associated with two index numeration of the gauge fields.
So it's really like a matrix model. This is the thing. It is in the limit when n goes to infinity, it becomes really, as I will show in a moment, becomes really the theory of 6 dimensions with a closed surface as the other two. And when n is finite, it is this fuzzy surface. It's like a matrix model on a surface. Now you can argue in this formulation, say in the previous one here, n is necessarily an integer, it says un, right? But once I write it this way, n can be anything, like any complex number, it's not necessarily an integer. So you can say you can define gauge theories outside SUN, say outside integers, any numbers, complex numbers. So does this mean anything? I have no idea. So the first part is a simple algebraic result. And in fact, it was proven first, as far as I remember, by Hoppe. Again, it was his thesis. By Jeff Goldstone was his supervisor. So at MIT thesis. And the best explanations are really in his thesis rather than in the papers. So you have to go to ask from the thesis of Hopper from MIT, and that's very well explained. So, so the statement is the following: the SUN algebra becomes at large n, when n goes to infinity, becomes the algebra of area-preserving diffeomorphism of a closed surface. In fact, I can prove it, say explicitly, for a sphere and a torus. And then you can argue mathematically by various mathematical theorems that it's true. Well, the sphere and the torus simply because you can have global symplectic coordinates explicitly for sphere and torus. For complicated surfaces, you have to rely on mathematical results, start making it locally and then expand and things like that. Okay. But it works. Okay. So the first proof is to prove that's what Hoppe did. The structure constants of the diffeomorphism of S2 are the limits for large n of those of SUN. So the algebra goes appropriately rescaled. I leave out the rescaling factors. But appropriately rescaled, the structure constants become the structure constants of the other group. So algebraic. Everything I say applies to classical field theories. I will make some remarks if you want to do it quantum mechanics. So it's just classical field theories. Forget about quantum field theory for the moment.
Structure constant of SU2 is not SU2 but S2, diffeomorphism S2
yes.
is something like, not structure constant, algebra is W infinity or what? Area preserving diffeomorphism
every preserved diffeomorphism, yes.
Infinity or something like that.
Something of that.
This one?
Yes, maybe. Yes. So alternatively, you can prove it instead of going through the proof of the structural constants, which you can see it the following way. Take a sphere, for example. The symplectic coordinates are theta and phi, cosine theta and phi. So let me define x1, x2, and x3. So I have the sphere, and if a point in space with x1, x2, x3, if I can write it this way, is on the surface of the sphere. Right? So you define the YLMs this way as polynomials in X with these symmetric and traceless tensors. And you can prove, this was Finger in old days, that you have exactly the 2L plus 1 linearly independent tensors for given L, right? Which are the, so you get the YLMs.
So it's spherical harmonics.
But yeah, the spherical harmonics. Right? So then what you do is that you have an SUN. Pick up an SU2, right, somewhere inside SUN. And you have, for every SUN, you can find SU2s. Right? So pick up an SU2, and then you define, which means these are the generators, right? And then these three generators, the same way that x1, x2, x3 were the basis for all the YLMs, right? You can expand the YLMs in powers of x1, x2. The same way, you can use this S1, 2, 3 to define all the SLMs, which are the generators of SUN. And you can prove that they satisfy these commutation relations with these structural constants, which are the SUN structural constants in a sort of peculiar notation. But these are. Now, then when n goes to infinity, you see immediately that this will become, if you rescale them appropriately, then you will have, under that norm, trace of x squared, the limit as n goes to infinity of the generators are three objects which commute, because these are 1 over n, the commutators, so they commute and they satisfy that. Right? So they are really points in a sphere. And then you work out all the details, and that's what you find out. It's a classical theory on a d plus 2-dimensional space where the other two, the way I did it here, are a sphere. And you can do the same thing with a torus by taking the appropriate choice of things, right?
So SU2 corresponds to this plus 2 extra dimensions.
Yeah, that's right. That's right. So, as I said, what is the quantum theory? I don't know, because this is a classical theory. If you try to do perturbation expansion, it was the work because the rescaling is not the one that would give you the planar diagrams. You have another, so the quantum theory is not easy to define. Presumably, and I will come back to it, is because you have not, I cannot implement the BRS transformations in this language. So I don't know exactly how to do the quantum theory of these theories. Now, suppose that I don't take large n, I keep n whatever it is, 2, 3, whatever, n, SUN, right? And then I claim the following thing, that I can define, I have two z's, z1 and z2. I define the tau plus, tau minus, and tau 3 this way. And then the claim is that if z1 and z2 satisfy this Heisenberg algebra, the TIs satisfy the SU2 algebra. And if the TIs satisfy the other way, if the TIs satisfy the SU2 algebra, the Z's satisfy the Heisenberg algebra. So the two statements are equivalent. Right. So if you assume the Heisenberg algebra for Z1 and Z2, you get the SU2 algebra for the T's, and then the construction we said before, you get all the SUN algebra for any n. You don't have to take the large n limit for that. Now, the same thing is with torus. I will go faster a little bit there. Well, you do the same thing. For SUN, we picked up an SU2 subgroup. The torus is a little bit special, so you pick up a quantum U1 cross U1. There is no U1 cross U1 subgroup for the SUN. So inside SUN, you pick up a quantum U1 cross U1. And you do it the following way. You define these matrices for fixed n, right? Omega is the, well, here I did it for n odd. You can do it for n even also. It's the nth root of unity. And you define those two matrices here. And then it's easy to check that g to the n equals h to the n equals 1. And then you have this quantum group commutation, hg equals omega gh. Right. And then, again, you use these g's to build all the SUN generators. And this is the explicit way you do it. S, M1, M2 is that. S dagger is that. And then you prove this computation relation, SM, SN. M and then now are M1, M2, and N1 and 2 here. That's what I mean. And then you find that as n goes to infinity, you find the diffeomorphism on the torus. And then Z1 and Z2 are the two angular variables on the torus when n goes to infinity, which are the symplectic coordinates on the torus. And then again, for arbitrary n, you define h and g this way. Z1 and Z2 satisfy this commutation relation, and H and G satisfy the quantum group commutation relations. And again, it works both ways. If H and G satisfy these commutation relations, the Z's must satisfy that and the other way. Right. So this is.
Complex structure of the torus?
Pardon? Excuse me?
Where does one see the complex structure of the torus?
Well, for the torus is very simple, because eventually you have to write what I have not written, the star product. right, for the fields. And then this is straightforward. You see, it's easy to do it for the torus because you have only those two. And then in the star product, you have this symmetry of the thing. It is more complicated for the sphere because then you have to symmetrize back everything. So the structure of the surface you end up, as I say, this works for any surface, but there is a different definition of the star product depending on the surface. And I can do it explicitly for the torus, it's simple. As an expansion, I can do it for the sphere, and I assume that it is true for the others, although I have not done it explicitly. It gets complicated. But really, the geometry of this surface comes through the star product. So you're right, thank you. So this is again, that's what I have to. Well, here are some remarks on this discrete subgroups of the Heisenberg group. People, have tried to use that in condensed matter physics and things like that. I will not go into it. It's interesting. So far for the large N approaches I have said, this is the thing I have been mostly involved personally, so that's why I spent some more time. In some sense, it is again an equivalence. It's not, you don't get anything new. You have a gauge theory, you can reformulate it as a theory on extra dimensions in which these two extra dimensions which satisfy non-commutative geometry. Does this buy anything for you? I don't know. For the moment, I have not seen any physical results coming out of that. It's just an equivalence. Maybe it's interesting, maybe it's not. So now I will go a little bit a step behind and try to see the whole picture, how it goes. And I will give you my ideas of that. What we have learned in physics in the last 40 years or 50 or whatever, now it's 50 in fact, is that gauge theories represent all the fundamental forces, describe all fundamental forces are gauge theories. And they are diffeomorphisms for space-time, and they give us general relativity, right? And they are internal gauge symmetries for internal symmetries, which give us the standard model. U1 crosses U2 crosses U3, right? Standard model. Somehow you say, okay, the first part is fine, they are all gauge transformations, so you are happy. But in fact, there is a dissymmetry. They are not symmetric, these things, because diffeomorphisms act. It's a symmetries of four-dimensional space, or whichever other space you have if you don't like four-dimensional. But let's stay with four-dimensional space. So diffeomorphisms are transformations that act on four-dimensional space. And they are gauge, what I was saying, in the sense that the parameters of the transformations, let's say translations, become functions of the point of x and t. Right? So this is the gauge part of it. Now, internal symmetries are transformations that act on a different space, not on x space. Right? So it's another space, which has dimensions depending on whichever symmetry you are looking, right? So for SU2, the Heisenberg isospin was three-dimensional space. Right? When you gauge these symmetries, the parameters become functions, but not of the point of this internal space. They become functions of x, of ordinary space. Right? In fact, we have lived with it for so long that we consider it obvious and natural. But let me remind you that this has puzzled the great names who did it before for many, many years. When the first person who tried to do SU2 gauge theories was Klein, and he did not do SU2 gauge theories as we do it today. He started with general relativity. In fact, he was doing it in 5 dimensions, but it was not very consistent what he was doing. But anyway, he did, in some sense, Kaluza-Klein, and then sent the gravitation to infinity, decoupled gravitation. So, strange way of doing theory directly. And Pauli, 13 years later, in 53, just before Young and Mills wrote their article, did exactly the same, except that he was doing it more consistently mathematically. He was starting from a 6-dimensional theory, compactifying on a sphere, and then he had SU2. And then again, decoupling gravity. Yeah. So, for many, many years, all this generation of physicists, the old ones, were so fascinated by general relativity that they could not conceive local transformations without diffeomorphisms. So for them, they were the same thing. So they were doing it with, and then somehow they sent the gravity away. And Young and Mills, as far as I know, were the first to understand that you don't have to do that. You can do it directly in flat space. But so we learned it this way, all of us, that we did it on flat space. But this hides the important thing that somehow we don't have this common view of gauge transformations. So now my question is there a space on which internal symmetry transformations act as diffeomorphisms? Can I really see it again? Kaluza-Klein is one way, right? And in fact, in most modern string theories, that's what they're doing. When they compactify, they try to guess the gauge symmetries of the standard model by the compactification, right? So the question now, I will ask it this way. Suppose that you don't go to string theory to extended objects or something. Just algebraic problem, purely geometric. Not algebraic, I mean geometric. Is there a space on which internal symmetry transformations all of them act as diffeomorphisms? Can I have? And the answer is yes, but it's a space with non-commutative geometry. So you can do that. It's a space with non-commutative geometry. It's a space defined by an algebra of matrix-valued functions. So this is probably the most physical motivation of really studying non-commutative geometry theories, is that somehow they seem to be the natural extension of having non-abelian gauge theories, and having in the back of one's mind that somehow we have to unify everything with gravity, which is also the gauge transformations are diffeomorphisms, so better find some way in which everything is diffeomorphisms. Right? So this is the motivation I want to pursue here a little bit. Now, some useful references are here that this has been pursued by many people, but in fact, it's fair to say that Alain Kohn was he's a mathematician, and he started it a little bit very many years ago, but as a mathematician, so not always with the motivations of the physicist, and it's also not very easy to read most of his papers. Well, I assume that you have heard about that probably more than you ever wanted to know from Slava, so it's okay. So I will try to give some idea about that. Now, the idea is the following. Let us start as a mathematician. So You see the Kahn's influence there. So you want to extend to find something that looks like a Heisenberg algebra, right? This is the, so Heisenberg algebra, you take X and you take P, right? The momentum, and you impose some commutation relation. So this is the algebra. So how can you extend that? What do you need to extend it? And after some discussion, which you will find in the paper, so they say that the construction really, in the most natural way, it involves what they call a fundamental spectral triplet. Now, what does it mean? First of all, you must have, since you do some quantum mechanics at the end, you must have some Hilbert space. Right? So it's obvious that this is obvious there. So you have a Hilbert space of functions, and you want to, you will have operators that act there, and the physical quantities are the spectrum of these operators, the eigenvalues of these operators. They will be the physical quantities. So this is the meaning of the one spectral triplet. So you need the spectrum of it. So you need, obviously, Hilbert space H. Now, what you need is something that plays the role of X, of positions, and something that plays the role of momenta, of D. Now, what would, and you don't want to have to define the space at the beginning, because then you lose the possibility of introducing non-commutativity and all that. So what is the natural way to describe a space? And for a mathematician, this is the algebra of functions that are defined on that space. So if somehow I give you the algebra of functions, and somehow you can think of it easily, right? Say the functions that are in physics, we are more used to think of transformations rather than functions that act on the space. So, for example, if you want to have something which is defines the four-dimensional space, it's enough if I tell you that translation invariance does that, right? And this goes back to the beginning of humanity. The oldest reference I found was in Euclid's statements. He understood that to define the plane or the space, you had to define just the symmetries, translations and rotations for the space. And this defined the space. So you see, in some sense, I don't know who was the first who extended this from transformations to the algebra of functions. You see, the algebra of functions is better than just the transformations, because it is more general, because the transformations assume that you have some metric. It's a metric space, right? If you want to translate or something, you need something like a metric. While if I give you the algebra of functions, you don't need to have a metric. It's some more general manifold, and you can. And in the simple case in which you find back the ordinary things you have. So it's a more general way to pardon?
You don't need even symmetries.
I can't hear you.
Not even symmetries.
No, symmetries you don't have even metrics, so you don't know. So it's a more general way to define the space is by looking at the algebra of functions that are there. And then you want, so this is, all the arguments I give you are just arguments. Don't consider them as proofs. At the end, you have to write down the theory and see whether it makes sense and whether it does what you want it to do. Right? All these are motivations, how to guess the right things. Then you have to find something that looks like the momentum, that replaces the momentum. And apparently for mathematicians, of the young mathematicians, not the old ones, for young mathematicians, the Dirac operator was obvious. And this is because they grew up after the Atiyah-Singer theorem, in which really you find the manifold is really described by the difference of eigenvalue, 0 modes right and left. Right? So the Dirac operator, for them, it is obvious. But you see, Dirac operator, again, has lots of structure. It's not just, first of all, you must have some spin structure in your space because you need a connection omega or something, gamma matrices, whatever, right, all that. And then the argument is that, well, Dirac operator is like the square root of the Laplacian. The Laplacian is like the inverse of ds square of the square of the distance. So this one will be like the ds, since the square is the square root. So in some sense, this will be the measure. The Dirac operator will replace the fact that you don't have necessarily a metric, but it is through the Dirac operator that you can define distances, short distances, not very long. Right? So this is the argument. So these are the three things that you pick up. You pick up the Hilbert space, the algebra of functions, and the Dirac operator. In fact, if you forget about gravity, chirality is enough, because in the Atiyah-Singer theorem, what you need is really the chirality operators, the right and left things. You don't need the entire Dirac operator. But it's this scheme for me, if you don't put gravity, it will be just a reformulation of known things. You will never get any. Alan Kohn and Ali Chamseddine had spent years and years trying to do it without gravity. I do not think they went very far. It's not interesting without gravity. So the important thing is to put also gravity. It calls for gravity. Now, again, that's what I was to explain. The Hilbert space is obvious, you need it. The algebra of functions replaces the space, because that's what, if you don't have a geometrical space with metric and all that, this is the closest you can go, right? And the Dirac operator plays the role of the inverse of distance. Then you have to, what the mathematicians call decorations. And once you, and these depend on the dimensions of space-time. Right? For example, the chirality operator is for even dimensions. Right? So you have a chirality operator, and then somehow you have to define what in field theory we have reality. What are the real functions that you have? So you remember in Whiteman axioms, for example, when you define field theory, you introduce the CPT operator as an axiom. So you need a CPT operator to define what is real. So this is, again, you need another operator there, which really it is what we call CPT. They call it charge conjugation, but really it is CPT, if you think clearly. So you need this operator, otherwise you cannot define really reality, which you need. So once you have all those, the rest is mathematics, complicated mathematics, very complicated, at least for people like me. Young people have learned more mathematics than I had learned. But these are the real physics assumptions that are behind. And well, gauge theories emerge naturally now with general relativity. If you try to play that game, because of this, you see, you have this algebra here. Where is the algebra? Here, oh, sorry, here it is. Because of this algebra of functions, right, you have to see what kind of solution, what kind of algebras you can get. You have several possibilities, but then you see immediately that you have matrix-valued functions. So you have gauge theories, which is a good thing. It's not, it is the other way of what often people do, what we do. They say, well, let us study general relativity. So we write the Lagrangian of general relativity, gauge invariant, and then if we want also fields, matter fields, we put them in. There somehow they come directly. The gauge, not any matter fields are different things, but gauge interactions come as part of gravity. You cannot separate them because they are part of the algebra. So this is, if it turns out that it is, well, there are several mathematical points that remain to be, but I think this is probably the most interesting part of that somehow there is a unified, naturally unified framework for gauge theories and gravity, and not any gauge theory, some gauge theories, if you specify the four-dimensional space. So that means for other spaces you have different. But for that, not any gauge theory, you have some gauge theories. And this may be the interesting thing. So you say, so what? After that, after I have said all that. Well, as I say, a possible way to unify gauge theories and gravity. Still, there is work to be done because the geometry is there, but not the dynamics, the field theory. Still, we have to develop the field theory of it in a complete way, and we don't know how to do it. It's not obvious. I will come back in a moment to that. Again, there is, you see, in this theory, you find in, with some modulo, some assumptions, you find directly the spontaneously broken phase of, say, the Higgs field, without having to put anything in the beginning. This reminds what you do in string theory, in which when you do, say, the brain engineering of the standard model, what we would call in the old days, you have 3 brains, right, in the 3-dimensional brains, and then the distance between brains is the Higgs field, is the mass of the Higgs field, is broken. When the brains are on top of each other, you have the exact symmetry, non-broken symmetry, and when you pull them apart, it is the thing. So this picture emerges in this way, and I have to say that as far as I know, it antedates, comes before the corresponding picture from string theory. So it was earlier than that. They had discovered it first. So this gives a possible connection. I say a possible connection because then when, like everything, when you try to do it, real calculations, it becomes very tricky and it's not clear what you get. I will come in a moment. The actual implementation brings us back to flat space calculations. That's too bad. We don't know how to compute directly in the non-commutative space in this way, right? So somehow we have to improve our mathematics in this respect. We don't know how to do it. For some time, there was a thing of new predictions for the standard model parameters. And although the predictions were not satisfied, and finally, still it raised an interesting question, which is the following. The standard model has 17 arbitrary parameters, and they are masses and coupling constants, right? And as we know in quantum field theory, masses and coupling constants are not calculable. We have to take them from experiment, right? That's a very simple thing. Can we reduce this number? Can we find the theory, the same theory, the standard model, because that's what works, but for example, can we impose a relation? For example, the relation that was used for years was mz squared divided by m Higgs squared to be equal to a constant. This was the first prediction of these theories. Now, is it possible to have that? Suppose that there is some unknown symmetry, some complicated thing, right, which gives that. We don't know it. We believe that the parameters are. You see, if Heisenberg were not here to tell us that there is isospin, the fact that proton and neutron are almost degenerate in mass, we wouldn't understand in some sense, right? So is that there's something like that. Could we find a relation with some kind of hidden symmetry or something in which mz square over mh square equals a constant, given constant. Now, in the standard model, this ratio is ratio of coupling constants, right? G1, G2, and lambda, the coupling constant. So the question is, can we impose some relation like that among coupling constants? Now, you can say, well, why not? I can assume it's there. But the idea is not only to impose it, is to show that it's stable, it's invariant under the renormalization group. Right? That it remains, if you impose it, it remains to all orders. So for that, you must find out, you have to check. The good thing about the renormalization group is that, at least in one or two loops, it does not depend on how you renormalize the theory. Do it whatever you want. The first terms in the beta function are renormalization independent, scheme independent. So this question has a clear answer. It's either true or false. So you compute the beta functions for that. Either you find a zero or you don't, right? And this is the, so you have a fixed point or you don't. Here are the beta functions for G1, G2, and lambda. You work out the thing, eta, etc. Then, oh, sorry, you went down. So this is the relation you want, Z. It's eta 1 plus eta 2, right? And you compute beta of Z, right, of this variable. And it has no zeros. It's positive definite. So there is no. So the standard model, this you can work it out with other relations, every relation you can think of. So the standard model really is an irreducible set of parameters. You cannot impose conditions, right? So if you try to have some predictions, they must come from somewhere else, not inside the standard model. Well, this is the BRS thing that non-commutative I was saying. Now, on the other hand, the standard model has become an extremely accurate theory, with something that people don't realize always. The accuracy reached by experiments as well as theoretical calculations, that's very important, made, you see, for example, MW is measured to be that. Now, you remember, you see what is this, precision. It's incredible. So if somebody comes and tells you, oh, I have a theory that has MW 81 GeV. Oh, well, 80.4 or 81, it's almost the same. You say, no, it's not. It's more than 20 standard deviations away. So it's a very, very precise theory. So if you have something to, some guess of what it is, it must be very precise, not just approximate things. There is no way to do it. So, what can we say? We see that somehow we must have some new physics. And we don't know what is this new physics. Non-commutative geometry was given, and I believe still gives a very good hint of which way we go. But somehow what is missing to me from non-commutative geometry is the possibility, at least the framework we have until now, which is the most complete framework we have, is this one here I told you, is we miss the possibility of have nilpotent operators, to add their operators that are nilpotent. Now, why do we need this? Well, first of all, we need them for fermions, because they are, but we need them for two reasons. One is BRS. If we want to make really quantum theory, we need BRS. And this has a charge which is nilpotent. And I don't see how to put them in this, to put it. And the second is my own prejudice, is supersymmetry. I believe that somehow we must be able to put supersymmetry in. So this comes to my final thing, is that all this smell like some particular kind of gauge of string theory, all these things. But I don't know how to make the connection. And one of the reasons I don't know how to make the connection is that string theories are naturally formulated with supersymmetry. And here I don't know how to put supersymmetry into the game. So this is new physics is around the corner, but we see no corner. So we don't know where it is. Conclusions. Non-commutative geometry has come to stay. As I say, it's part of gauge theories. You cannot say, you may not like it, but it is part. It's not a new ingredient, it's there. So now, however it will turn out to be convenient for us to use, it's another formulation of gauge theories. It's not a new thing. Now, whether it will be convenient for us to use or not is still questionable. We don't know. For the moment, we don't know what it is. It will depend on our ability to simplify the mathematics. That applies to people like me who don't know so deep mathematics, or to master them deeply, others who know more, to really get new insights. For the moment, the only physical insight I have seen in these things are a new way to look at, say, dark energy or dark matter, things like that. You have a new insight there. So this may be interesting, but that's the only thing. It's not really in the quantum level, it's in the classical level. So maybe we need something more. So thank you very much. That's all I have. One of the problems I have is hearing.
This non-commutative geometry of Common charges.
Yes.
Is there a natural scale for non-commutativity?
Well, it is if you want to. Yeah, it's a Planck mass. Yeah, Planck mass. If you want to put it together with the, you see, what they prove is that the solution of these equations, the non-commutative. In their language, this is mathematics, quantum mathematics. They define a certain trace for these product operators, where they have these commutators on it. And they try to find solutions of that have these two decorations, I said, the gamma 5 and the CPT. And they find that the space splits into blocks. And the natural scale of that is the Planck scale, if you have. So I believe that this is the natural scale they will have for non-commutative.
Yes. There used to be the prediction of the Higgs mass.
Yes.
So what has ended in the wrong way?
Well, there is a physical answer and the technical answer. The physical answer is what there is no possibility of predicting. Of course, it was a classical theory, so you can say that. Now, the technical thing is that this prediction went away because really the terms they were using were not really the most general terms they had. They had other terms, which they had dropped at the beginning. Now, I'm not convinced that this once you put them in, you have an extra parameter that you can work out and somehow it works. I'm not convinced that this is the right answer, because these extra terms that they have are the same ones that give also masses to neutrinos. Now, to a physicist like me, saying that the mass of the Higgs, what it is, depends on the neutrino masses, I don't believe. Okay. So I believe that this is not the right answer, but on the other hand, this model should be taken as an example, not as a real. The real thing should be when the Dirac operator is really the Dirac operator, not just gamma phi. Right? In which case, really, you will have general relativity and all that. So somehow you have to work out the details of the general model, and I don't know exactly how to do it. And of course, the most important thing is, can you do really quantum field theory with it? Which I don't know. So there is still lots of work to be done in that. Anyway, this particular prediction went away. So.
Yes.
Through the large SUN, large N SUN theory,
Excuse me?
through the large large N SUN theory,
Yes.
sounded like the you were saying the non-commutative structure on a torus and on a sphere are
Right.
equivalent?
No, because the structure, yes, locally, Z1 and Z2, they have the same commutator. But if you want to, locally, they are all the same. It's the two fuzzy surfaces. But if you want to prove the global structure, then this will come from your definition of the star product. And the star product is different in the two cases. So,
Yes.
When you talk about the scale theory, there were always these two experiments, Z1 and Z2, why two and not more or less?
oh, the two come in this particular, in the formulation I gave, it's because the gauge fields belong to the adjoint representation, so that's a matrix with two means. But yeah, it's not, this you have to see it only as an extension of ordinary gauge theory. It's not really as a non-commutative geometry deep. There you have really to do more mathematics. This is the trivial part, not the...
Yes.
Yes. Sorry.
Speak loud because
So I was wondering, what are the minimal ingredients you need to define non-commutative geometry, and whether the star product is contained?
Well, in the minimal ingredients, I think, is what was there, the triplet, the Hilbert space, the something that looks like the Dirac operator or maybe something else, and something like the algebra function.
But presumably this
But as you say,
contains commutative stuff as well.
yes, that's right. Yes, no, the algebra functions is a matrix valued algebra, so it's not commutative. So the non-commutativity comes from
What
that.
are these functions?
Well, then this depends on what you put as in your non-commutation relations, the extension of the Heisenberg thing. If you take only the chirality, forget about gravity, right? So you have chirality and algebra. Then the claim is that there are only some algebras that are consistent with this scheme. And these some algebras contain this what we want for the standard model. But I don't know the proof of this statement.
one algebra is N for C,
Yeah, exactly.
and the other algebra is N
Two
for
on,
H.
on quaternions. I don't know the proof of that. I see why these ones work, but I cannot prove that others wouldn't. And they don't say that others don't work. So I don't know exactly what they say. Maybe you know.
No,
You know.
then the others will not work if you want to get manifold with an arbitrary topology.
Yeah, maybe this.
You see, because at the beginning, when the whole thing was started, okay,
Yeah.
it was related with this mapping, yeah. But in this case, one could get only topologies which would consist of
Disconnected.
bubbles
Yes.
of the
Yes.
about one scale. But to get arbitrary topology in four-dimensional case, you have to
So
have
somehow
one.
the algebra is, this is a very interesting part. I have only an engineering understanding, not a deep understanding of it. Why all of a sudden this algebra? I don't know.
Deep is only Allah who actually requires 3 months to prove this.
Yeah,
It shows
exactly.
only
It
4
took,
dimensions.
by the way, yeah, that
4
depends.
or less
This
dimensions.
depends on the dimensions.
4, 3, 2, it looks like it doesn't work in 5, 6.
Is that even comparable to the weak gravity conjecture?
Comparable to the gravity conjecture.
Is there anything comparable to the weak gravity conjecture?
I don't know.
What is the gravity conjecture?
It's like a lower bound communication of
Yeah.
this weak gravity.
Yes.
You mean that you don't think about it?
Yes, exactly. Yes. I don't know. Maybe he knows.
Here, all the calculations that you use
Yeah.
theory is not quantized in terms of the fields.
Yeah.
But by the way, string theory is also not quantized.
String
in
theory
terms
is the
of
same, yes.
fields.
String
You are
theory
doing
again,
it
yes.
in
Yeah, but you have an algorithm to impose this, say, what people would call in the old days first quantization.
Yeah, yeah.
In the old days they had strange names, but you have an algorithm. Here still you have to invent the algorithm.
No, it's the same story. Okay, you just put heads on the field.
No, because this is not, well, I
I
have
know
we can
that,
discuss.
John, I know that it's not actually within this.
Yeah, exactly.
This is what people are by the way also in string theory. Because,
Anyway, it is, there is still lots of work to be done to my appreciation, to clarify everything that is. First of all, whether there is real new physics in this thing, and what is the connection with whatever other physics we know. Like, I wanted to see also the connection with string theory, for example. I'm not convinced that there is no connection. I believe there is a connection. But, and there are some strange things. The 10 dimensions also appear there and there. It's strange coincidence. So I want to understand.
Okay.
Yes.
Isn't this star product which you
Yes, yes, yes.
It looks very ill-defined.
Very defined, yes. Arbitrary things. You have to symmetrize things. I don't know of any other way of doing it.
No, but he don't
Yes.
use any stuff for that.
Not in quant thing, he does not use that. You use it if you want to do field theory, ordinary field
Right.
theory. Then you have to use something to define products, right? But not in things.
Divergences are going to be quite.
Oh yes, then there are divergences because when you expand, you get new. This, however, has been addressed in ordinary. People have done just simple thing. Take 5 to the 4th or whatever theory you want, put it in a space with x nu, theta mu nu, high theta mu nu, and try to work out the thing. This has been done. And they have proven that although, as you say, it produces new divergences, you can still renormalize the theory. It's a renormalized.
Does theta get removed?
Yeah, exactly. So you will normalize it. It's nothing exciting because the theory you started with was normalized in the first place. It's nothing new. But it can be done, ordinary things. But it doesn't give you anything new. It's just another way to
It gives you headache.
it gives it doesn't. It has not really solved any problem. You see, at the beginning, the idea was you put non-commutative geometry and there are no divergences. Maybe it is still true if you know how to compute in a different way. But if you expand in powers of theta, the divergences are still there. Fine.